Download this code from codegive.com, link in the description below. A complete guide to graph representation with graphblas, a sparse matrix approach. While vector databases excel at similarity searches in dense vector spaces, they often fall short when dealing with complex relationships and graph-structured data. This is where graphblas and sparse matrix representations come in. Graphblas is a standardized API for building graph algorithms using linear algebra, specifically sparse matrix operations. This approach allows you to leverage highly optimized linear algebra libraries, like suitesparse graphblas, for efficient graph processing. This tutorial provides a comprehensive guide to representing graphs as sparse matrices and using graphblas for various graph algorithms. We'll cover Understanding the fundamentals. *A. Why graphblas and sparse matrices? *B. Graph representations, adjacency matrix. *C. Sparse matrix formats, Q, CSR, CSC. *D. Graphblas concepts, semirings, operators, descriptors. 2. Practical implementation with suitesparse graphblas, C++. *A. Setting up suitesparse graphblas. *B. Creating and populating sparse matrices for graphs. *C. Basic graph operations, degree calculation, traversal. *D. Advanced graph algorithms, PageRank, connected components. 3. Comparing with vector databases. *A. Strengths and weaknesses of each approach. *B. Use cases for graphblas versus vector databases. Understanding the fundamentals. A. Why graphblas and sparse matrices? Exploiting sparsity. Real-world graphs are often sparse, meaning they have far fewer edges than possible, and 2 for a graph with n nodes. Sparse matrix representations efficiently store only the non-zero elements, edges, saving significant memory and computation. Leveraging linear algebra libraries. Graphblas allows you to express graph algorithms as linear algebra operations on sparse matrices. This enables you to utilize highly optimized linear algebra libraries, like suitesparse graphblas, a reference implementation, that have been meticulously engineered for performance. These libraries often have hand-tuned assembly code for specific CPU architectures, resulting in substantial speedups. Parallelism. Linear algebra operations are inherently parallelizable. Graphblas libraries are designed to exploit multi-core processors and even GPUs, leading to further performance gains. Standardization. Graphblas provides a standardized API, making graph algorithms more portable and reusable across different platforms and libraries. Expressiveness. Complex graph algorithms can often be expressed concisely and elegantly using graphblas operations, promoting code clarity and maintainability. B. Graph representations, adjacency matrix. The core idea is to represent a graph as a matrix, where rows represent source nodes. Columns represent destination nodes. A non-zero element at matrix row, COL indicates the existence of an edge from node row to node COL. The value of the element can represent the edge weight, example distance, similarity, capacity. Directed versus indirect graphs. Directed. The matrix is not necessarily symmetric. Matrix I, J can be non-zero, while matrix J, I is 0, or a different value. Indirect. The matrix is symmetric. Matrix I, J and matrix J, I are both non-zero and have the same value. Asterisk weighted versus unweighted graphs asterisk. Asterisk unweighted asterisk the value of a non-zero element is typically 1, or a Boolean true, simply indicating the presence of an edge. Asterisk weighted asterisk the value of a non-zero element represents the weight of the edge. See sparse matrix formats, Q, CSR, CSC. Storing a dense adjacency matrix for a large, sparse graph is highly inefficient. Sparse matrix formats are designed to store only the non-zero elements and their indices. Asterisk 1. Coordinate list, Q. Asterisk stores a list of row, column, value, tuples for each non-zero element. Asterisk simple to create and understand. Asterisk not ideal for efficient matrix operations due to lack of ordering. Asterisk 2. Compressed sparse row, CSR. Asterisk efficient for row-wise operations, example multiplying a matrix by a vector. Asterisk stores the matrix in 3 arrays. Asterisk values, array of non-zero values, stored row-wise. Asterisk col underscore indices, array of column indices corresponding to the values. Asterisk row underscore pointers, array of pointers to the beginning of each row in the values and col underscore indices arrays. Row underscore pointers I indicates the start of row I, and row underscore pointers I plus 1 indicates the start of row I plus 1. The difference row underscore pointers I plus 1, row underscore pointers I gives the number of non-zero elements in row I. Asterisk 3. Compressed sparse column, CSC. Asterisk efficient for column-wise operations. Asterisk similar to CSR, but stores the matrix by columns. Example, representing a graph as a CSR matrix. Consider the following directed, unweighted graph with 4 nodes and 4 edges. The corresponding adjacency matrix would be. The CSR representation would be. Asterisk values, 1 1 1 1. Asterisk col underscore indices, 1 2 2 3. Asterisk row underscore pointers, 0 2 3 4. Explanation. Asterisk row 0, starts at index 0 in values and col underscore indices. It has 2 non-zero elements, values 0, 1, at column col underscore indices 0, 1, and values 1, 1, at column col underscore indices 1, 2. Row underscore pointers 1, 2, indicates the end of row 0. Asterisk row 1, starts at index 2 in values and col underscore indices. It has 1 non-zero element, values 2, 1, at column col underscore indices 2, 2. Row underscore pointers 2, 3, indicates the end of row 1. Asterisk row 2, starts at index 3 in values and col underscore indices. It has 1 non-zero element, values 3, 1, at column col underscore indices 3, 3. Row underscore pointers 3, 4, indicates the end of row 2. Asterisk row 3, starts at index 4 in values and col underscore indices. It has no non-zero elements. Row underscore pointers 4, 4, indicates the end of row 3. Graphblas concepts, semirings, operators, descriptors. Graphblas provides a powerful abstraction for building graph algorithms. The core concepts are asterisk semirings asterisk a semiring defines how values are combined during matrix multiplication. It consists of 2 operators. Asterisk multiply operator asterisk used to combine values along the edges. Examples, grb underscore plus underscore int 64, addition, grb underscore times underscore int 64, multiplication, grb underscore land underscore bool, logical n. Asterisk add operator asterisk used to accumulate the results of the multiply operator. Examples, grb underscore plus underscore int 64, addition, grb underscore max underscore int 64, maximum, grb underscore lore underscore bool, logical OR. The notation for a semi-ring is, add, multiply, on a specific data type. For example, plus, times, on integers, or, lore, land, on booleans. Asterisk examples of common semi-rings asterisk. Asterisk, plus, times, standard matrix multiplication. Used in many graph algorithms, path counting, shortest paths. Asterisk, lore, land, Boolean matrix multiplication. Used for reachability queries, connected components. Asterisk, plus, min, minimum cost paths. Used in shortest path algorithms, like Dijkstra's. Asterisk, max, plus, maximum capacity paths. Asterisk operators asterisk functions that perform operations on data. Asterisk binary operators asterisk take two inputs and return a single value. Used as multiply and add operators in semi-rings. Example grb underscore plus, grb underscore times, grb underscore min, grb underscore max, grb underscore eq. Asterisk unary operators asterisk take one input and return a single value. Used for applying transformations to matrix elements, example negation, absolute value. grb underscore ainv underscore fp64, grb underscore identity. Asterisk descriptors asterisk control the execution of graphblas operations. They specify things like asterisk masking asterisk used to selectively update elements in the output matrix. Asterisk complementing asterisk inverting the mask. Asterisk transposing input matrices. Asterisk structure slash value asterisk treating the matrix as a pattern, only structure matters, or a value matrix. 2. Practical implementation with suitesparse graphblas, C++. A. Setting up suitesparse graphblas. 1. Download and install asterisk. Asterisk go to https://github.com/drtimothyaldendavis/suitesparse, https://github.com/drtimothyaldendavis/suitesparse. Asterisk follow the installation instructions for your operating system. On Linux, this typically involves cloning the repository, navigating to the graphblas directory, and running make install. Asterisk ensure that the installation puts the graphblas.h header file in a directory that your compiler can find, example /usr/local/include, and that the libgraphblas.so library is in a directory that your linker can find, example /usr/local/lib. 2. Include and link asterisk. Asterisk in your C++ code, include the graphblas.h header file. Asterisk when compiling, link against the graphblas library. B. Creating and populating sparse matrices for graphs. Explanation asterisk. 1. grb underscore init, grb underscore non-blocking, asterisk initializes graphblas. grb underscore non-blocking enables asynchronous execution, potential performance improvement. 2. grb underscore matrix underscore new, and a, grb underscore bool, n, asterisk creates a new sparse matrix A of type grb underscore bool, boolean for unweighted, with n rows and n columns. 3. Edge definition asterisk the rows, cols, and values vectors define the edges of the graph in Q format. 4. grb underscore matrix underscore build, asterisk builds the sparse matrix A from the CU data. grb underscore replace tells graphblas to discard any existing data in A and replace it with the new data. 5. Printing the matrix. The code extracts tuples from the sparse matrix and prints them out to verify the creation of the matrix. 6. grb underscore matrix underscore free, and A, asterisk deallocates the memory associated with the matrix. 7. grb underscore finalize, asterisk finalizes graphblas. See basic graph operations, degree calculation, traversal. 1. Degree calculation. The degree of a node is the number of edges connected to it. In a directed graph, we have in degree, number of incoming edges, and out degree, number of outgoing edges. Explanation asterisk. 1 grb underscore vector underscore new, and out underscore degrees, grb underscore int 64, n, asterisk creates a new vector out underscore degrees to store the degrees. We use grb underscore int 64 to store the degree counts. 2 grb underscore matrix underscore reduce, asterisk reduces each row of the adjacency matrix A to a scalar using grb underscore plus underscore monoid underscore int 64. This semi-ring effectively sums the number of non-zero elements, edges, in each row, giving the out degree. 3. Transpose for in degrees asterisk in degree is calculated on the transposed matrix. 4. Descriptor for transposition, a descriptor is set to transpose the matrix. 5. Extract and print asterisk the final steps involve extracting the contents of the computed degree vector to print. 2. Traversal, single source reachability. Determine which nodes are reachable from a given source node. We can use Boolean matrix multiplication, using the LOR, land, semi-ring, to perform graph traversal. Explanation asterisk. 1 grb underscore vector underscore new, and reachable, grb underscore bool, n, asterisk creates a Boolean vector reachable to track reachable nodes. 2 grb underscore vector underscore seat element, reachable, source underscore node, true, asterisk initializes the reachable vector by setting the source node as reachable. 3 iteration asterisk the while loop iteratively explores the graph. 4 grb underscore vxm, asterisk this is the core of the traversal. It performs the operation, reachable equals reachable, reachable asterisk a, using the LOR, land, semi-ring. Asterisk reachable asterisk a effectively finds all nodes that are reachable from the current reachable nodes in one hop. Asterisk reachable, reachable asterisk a, combines the new reachable nodes with the previously reachable nodes. This builds up the set of all reachable nodes. 5 Reachability update, checks to see if the reachability set has grown. If not, we are finished. 6 Output, prints the reachable nodes. 7 Cleanup, frees allocated memory. D Advanced graph algorithms, page rank, connected components. Illustrative outlines, code examples would be extensive. 1. Page rank. Page rank is an algorithm that assigns a numerical weighting to each element of a hyperlinked set of documents, such as the World Wide Web. Asterisk key idea asterisk a node's page rank is proportional to the sum of the page ranks of nodes that link to it, scaled by the out degree of the linking nodes. Asterisk graphblas implementation asterisk. 1 Damping factor asterisk introduce a damping factor d, typically 0.85, to account for the probability that a user randomly jumps to another page. 2 Normalization asterisk normalize the adjacency matrix such that the sum of each column is 1, this represents the probability of transitioning from one node to another. Handle dangling nodes, nodes with no outgoing edges, by distributing their page rank evenly to all nodes. 3 iteration asterisk iteratively update the page rank vector using the following formula. Page rank equals d asterisk, a asterisk page rank, plus, 1, d, slash n. Where asterisk is the transpose of the normalized adjacency matrix. Asterisk n is the number of nodes. For convergence asterisk iterate until the page rank vector converges, i.e., the changes in page rank values become sufficiently small. Asterisk semi-rings asterisk the, plus, times, semi-ring is used for the matrix vector multiplication. 2. Connected components. Find groups of nodes that are reachable from each other. Asterisk key idea asterisk assign a unique component ID to each node. Initially, each node has its own component ID. Iteratively update the component ID of each node to be the minimum component ID of its neighbors. Asterisk graphblas implementation asterisk 1 initialization asterisk create a vector component underscore ids where component underscore ids I is initially equal to I. 2 iteration asterisk update each node's component ID using the following operation. Component underscore ids equals min, component underscore ids, a asterisk component underscore ids, where a is the adjacency matrix. This propagates the minimum component ID from neighbors to each node. 3 convergence asterisk iterate until the component underscore ids vector converges, no more changes. Asterisk semi-rings asterisk the, min, times, semi-ring can be used in the matrix vector multiplication to propagate the minimum component IDs. Alternatively, a custom semi-ring can be defined to directly compute the minimum component ID between the current node and its neighbors. 3. Comparing with vector databases. A strengths and weaknesses of each approach. Feature graphblas, sparse matrix, vector databases. Data model explicit graph structure, nodes and edges, implicit relationships based on vector similarity. Query type graph traversals, pathfinding, connectivity analysis similarity search, nearest neighbor retrieval. Sparsity excellent for sparse graphs performance degrades with high dimensionality and sparsity. Relationships captures explicit relationships, ideal for relational data infers relationships based on vector embeddings, can miss subtle or complex connections. Scalability scales well with large, sparse graphs scales well with large data sets, but less efficient for complex graph queries. Explainability transparent graph structure, easy to interpret results black box embeddings, difficult to understand the reasoning behind similarity scores. Updates relatively expensive to update graph structure efficient for adding and updating vectors. Complexity requires understanding of linear algebra and graphblas API easier to use for simple similarity searches. Algorithms highly optimized for graph algorithms focus on vector similarity and nearest neighbor search. B use cases for graphblas versus vector databases. Asterisk graphblas asterisk. Asterisk social networks asterisk analyzing connections, finding communities, detecting fraud. Asterisk recommendation systems asterisk collaborative filtering based on user interactions, knowledge graphs. Asterisk cybersecurity asterisk analyzing network traffic, identifying malicious activities. Asterisk bioinformatics asterisk analyzing protein-protein interaction networks, drug discovery. Asterisk route planning asterisk finding shortest paths in road networks. Asterisk knowledge graphs asterisk reasoning over structured information. Asterisk vector databases asterisk. Asterisk image search asterisk finding similar images based on visual features. Asterisk natural language processing asterisk semantic search, document similarity, chatbot responses. Asterisk audio/video analysis asterisk finding similar audio clips or video segments. Asterisk product recommendations asterisk suggesting similar products based on user browsing history. Asterisk personalized advertising asterisk targeting ads based on user interests. In summary asterisk use graphblas when you have explicit graph data and need to perform complex graph algorithms that leverage the graph structure. Use vector databases when you have high-dimensional data and need to perform similarity searches based on vector embeddings. The choice between graphblas and vector databases depends on the specific requirements of your application. If your data is inherently graph-structured and you need to perform complex graph algorithms, graphblas offers significant advantages in terms of performance and scalability. If your data is high-dimensional and you need to perform similarity searches, vector databases are a better choice. Often, a hybrid approach, combining the strengths of both techniques, can be the most effective solution. For example, embeddings of nodes in a graph might be stored in a vector database and then used with graphblas for graph-aware recommendations. The key is to carefully analyze your data and your query requirements to choose the approach that best meets your needs.